For this lecture, we will discuss unit vectors. So a unit vector is defined as a vector that has a magnitude of 1 with no units. Its sole purpose is to point to a direction or to describe a direction in space. So last time we learned that there are different types of directions. So there are 3 forms of directions we use. Using the cardinal direction alone, a cardinal direction with an angle, and polar coordinate angles. This time, we will now have unit vectors as our direction. So, what is the difference of unit vectors compared to these other directions that we are using? Because unit vectors can be used in 3-dimension problems. Okay, unlike in cardinal directions and polar coordinate angles, these are only limited in a single plane or in a 2-dimensional plane. Let's talk about how can you represent a unit vector in 3-dimensional. So let's focus first in 2-dimensional, then I will introduce you the 3-dimensional. We know in a Cartesian plane, this is x, this is y, this is negative x, and this is negative y. Okay, so instead of using x, negative x, y, or negative y, or east, north, west, south, or polar coordinates, we will now use our directions, which are, so instead of x, our direction will be, for x is I hat. Okay, so that is, again, a unit vector has a value of 1, and it is used to point for a direction. So if I have here a vector that is 5 meter per second east, okay, so for example, I have a vector which is 5 meter per second east, so I will write it in unit vector as 5 meter per second I hat. Okay, so instead of is I hat. Now, since this is I hat, this is negative I hat. For y direction, so this will be called now as j hat. And for the negative y, this is negative j hat. Now, as I said, there is a 3-dimensional, okay? So, since we cannot properly draw a 3-dimensional direction in a paper, so for example, this is a vector, okay? If the vector is going out of the paper, so if it's going out the paper, so that is positive z, okay? So again, if the vector is going out the paper, that is positive z. If the vector is going inside the paper, that is negative z. So let's assume this is that one. So if the vector is going out, okay, the paper, so this is going out, so that is our z, okay? And if it's going inside the paper, that is negative z. Now, we represent this as if it's going out, okay, in this direction, we will use k hat. If it's going out, it's positive. If it's going inside the paper, that is negative k hat. So, for now, we will focus on how to convert from this direction into a unit vector. Okay, so that is 2-dimensional. So that will be, for example, let's go to vector C. Let's convert that one. Vector C is equal to 17.8 Newton south. Okay, so instead of using polar coordinate angles or directional angles, so from the origin going to south, so this is my vector C. So it means if we will use unit vector which has a direction of, so my vector C now can be written as 17.8, since that is south, that is negative j hat, or this is negative 17.8 j hat, and parenthesis, that is Newton. Okay, so usually the unit is outside the parenthesis. Okay, so let's go to another one. So let's have the example of vector A. So our vector A now is, okay, so that is 72.4, 32 degrees is of north. In this type of problem where there is a combination of polar angle and directional angles, so I have to convert this first to polar coordinate angles since we already solved this one last time. So this is also 72.4 Newton, 58 degrees. So if we will go back here, if I will explain it again, so why it is 58, because this one, okay, so our vector is 32 degrees east of north, so coming from north going to east, so that is our vector A, and that is 32 since our polar coordinate needs an angle from positive x, which is this, going here. Since this is 90 minus 32, that is 58 degrees. Okay? So, why we need to convert it to polar coordinate? Because we will use this to find the components of, for our vector A to have the direction of I, J, and K if there is a three-dimensional. For the formula of this, so our force has this form. So, in which, for this, A is equal to AX I hat plus AY J hat, or if there is a Z, so AZ K hat. This is the general form of our Cartesian vector notation. Okay, so if you will solve for the components, so what is AX and what is AY? So we know that to get AX, so that is just, okay, so that is AX is just equal to, what is the magnitude of A? Okay, cosine angle. The angle should be in polar coordinate. While AY is equal to the magnitude of A sine angle. Again, these are the general forms. So if this is a B vector, it will be BX I hat plus BY J hat. BX is equal to B cosine theta and BY is equal to B sine theta, or any letters. Okay, so this is a general form. Hence, if I will now substitute, okay, all my values, so we already solved this in component method, so that will be, my vector A now is 38.37, okay, I hat plus 61.40 J hat, and parentheses, that is Newton. Okay, so if I will put that in our Cartesian plane, so here we will have the axis first. Okay, so this is your I, and this is your J. Since it is lying on positive I and positive J, so we expect that is between positive I and positive J. So in this one, okay, this is almost the same in our graphical method. I'm doing this so that if ever the unit vectors are given and you are asked to draw this in Cartesian plane, you know how to do it. Okay, so let's use a scale, which is 1 cm is equal to 10 Newton. Hence, your AX, which is 38.37, is 3.837 cm, and your AY is equal to 6.140 cm. Okay, So let's draw. So first, we have to determine in what quadrant can we find positive I and positive j. So that is in first quadrant, definitely. Then the second one, we have to make a scale to represent the magnitude of ax and ay. So these are our scale and these are the length of our ax and ay. So we now draw first our ax. So that is 3.8. Okay, so that is the length of our ax. So from here, going here, that is your ax. Okay? Now, for ay, so that is 6.14. So here, 6.14. So 6.1. So here. Okay, so let's write ay. Okay, so I will just extend this one, this mark. Okay, until here. And I will also extend this mark going here. Okay, so in that case, this should be the end of my vector A. And my vector A now is... Okay, so that is 7.2 or 7.1. Okay, so this is my vector A, which is 7.2 or 7.1. So if I will write here, say my vector now A is 7.2. So let's say 7.2 cm. So that is roughly in Newton, that is 72 Newton, which is based on our given, our vector A is really 72.4 Newton. So we are just reversing the method that we do from this one, cardinal direction with an angle, going to the unit vector. So as your activity, please try to convert vector B from cardinal direction with an angle, going to polar coordinate, going to unit vector, and try it to draw in a Cartesian plane like this. Okay? So that is for single vector.